For the last few years, interacting with AI has felt a lot like using a really, really advanced vending machine.
Right.
You walk up, you type a prompt, and a single item drops out. You read it, you evaluate it, and, well, if you want something else, you have to stand there and type another prompt.
Exactly.
You are the operator, and frankly, you are the bottleneck.
Yeah. I mean, the industry actually refers to that as a highly transactional relationship. One human input equals one machine output. It's completely tethered to human typing speed.
But if you look at what just happened between April 19th and April 25th of 2026, that era officially ended.
It really did.
If you are tracking the global flow of compute, this specific week marks the exact moment the AI industry stopped talking about single prompt software and, fully pivoted to autonomous agents.
100%.
We are talking about a week where NVIDIA hit a $5 trillion market cap, massive rack-scale data centers were announced, and physical robots were deployed on factory floors. The vending machine is gone. We are now handing the keys over to the factory manager.
It represents a profound structural shift toward continuous agentic infrastructure. The systems being deployed right now, they don't just answer a question and go to sleep.
Right.
They think, they plan, and they execute over long time horizons.
Welcome to the Deep Dive. Our mission for you today is filtering through the absolute noise of NVIDIA's busiest week to understand this massive transition.
There is a lot to cover.
There really is. We are going to look at the research breakthroughs, the infrastructure melting down, and the enterprise adoption that proves this is actually real, because it fundamentally changes everything about how you will work and build. Okay, let's unpack this.
Sounds good.
To build that autonomous factory, you first have to rewrite the physics of how the machines think. Because if an AI is going to work on a problem all day long, it needs a way to remember what it did 3 hours ago without just crashing the server.
Yeah, the standard way we handle that is the context window. It acts like the model's short-term memory, basically.
Okay.
Historically, if you give an AI a massive document, every new word it generates has to mathematically look back at every previous word in that document using an attention mechanism.
And that takes a lot of compute.
A massive amount. The longer the conversation goes, the heavier the computational burden becomes until the system just crawls to a halt.
But on April 23rd, the NVIDIA technical blog published a global update under the headline Reimagining LLM Memory.
Right, the TTTE2E paper.
Yeah, which stands for Test Time Training with an End-to-End Formulation. When I was reading through this paper, the solution seemed almost like science fiction.
It is pretty wild.
Instead of holding all that context in a temporary short-term memory window, the LLM actually compresses the information directly into its own neural weights via next token prediction. It alters its own brain structure as it reads.
Think about the difference between, say, a worker trying to hold a massive 10-foot-tall stack of papers in their arms while walking around an office.
It sounds terrible.
Right. That is a traditional context window. It gets heavy, they drop things, and they move incredibly slowly.
Okay, so what is TTTE2E like?
It's like the worker sitting down, reading the papers, memorizing the facts by physically forming new connections in their brain, and then walking into the meeting empty-handed but fully informed.
It's like an AI actually learning and absorbing a textbook as it reads, rather than having to scan the entire index every time you ask it a question.
Exactly. They aren't carrying the data anymore. They have learned it.
And the performance metrics attached to this are what really stand out to me. On an H100 GPU, this method runs 35 times faster than full attention at a 2 million context length.
And that is huge. Decoupling the per token cost from the context length is basically the holy grail for long-running agents.
Why is that the holy grail specifically?
Because maintaining a constant inference latency, meaning the model responds just as fast at the end of the day as it did in the morning, is the only way an AI agent can effectively manage your email, calendar, and project files continuously.
So the memory bottleneck is being solved. But memory is only half the equation, right? If an agent is running autonomously all day, it also has to make complex decisions. It needs reasoning.
It does.
And that leads us directly into another massive paper published on April 24th globally at the ICLR conference. The headline was Test Time Alignment via Textual Model Predictive Control, brought forward by researchers from NVIDIA and NYCU.
A really important paper.
Now, I have to admit some confusion here. When I see the phrase model predictive control, my brain immediately goes to mechanical engineering. Wait, so we are using old-school robotics math to control language models?
We are. What's fascinating here is how it shifts the paradigm from prompt engineering to defining high-level goals.
Mm,
It illustrates a brilliant cross-pollination between physical engineering and software.
how so?
Well, traditionally, language models are aligned using heavy reinforcement learning before you ever use them. They are trained for months, so they hopefully behave well.
Right?
But this new framework adapts classical control theory directly to text generation at test time, meaning while the model is actually running.
How does that actually work in practice, though?
Imagine driving a car. You don't just lock the steering wheel in one position and hope you reach your destination.
Obviously not.
You look a few feet ahead on the road, you evaluate your trajectory, and you make micro adjustments to the steering wheel continuously to stay in the lane. Textual model predictive control does exactly that for language.
Okay, I follow.
Before the AI prints the next word, it evaluates the potential future trajectories of the sentence, scores them against the high-level goal you gave it, and corrects its course in real time.
Wow. So it's shifting the burden entirely. You no longer have to perfectly engineer a hyper-specific prompt to lay down the train tracks. You just hand the AI a steering wheel, give it a destination, and it navigates the obstacles itself.
Exactly.
And speaking of applying physical math to AI, we saw this scale up to a planetary level on April 22nd. NVIDIA published a global blog post detailing their Earth Day 2026 AI milestones, heavily featuring Earth-2's HEAL-DA data assimilation model.
Yeah, the tsunami forecasting system.
Right, an ACM Gordon Bell Prize-winning system developed with academic partners.
The core of that achievement relies on solving what scientists call the inverse problem.
The inverse problem.
Yeah, normally, predicting a wave involves taking the source of an earthquake and running a massive, complex, forward simulation to see where the water will go.
Okay.
The inverse problem works backward. You take the real-time sensor data from a buoy that just detected a wave, and you calculate backward to figure out the exact characteristics of the source. Doing that live usually takes too long.
But the researchers used GPU-accelerated pre-computed wave equations. Because they crunch the physics of the ocean ahead of time, when the sensor detects a wave, the AI simply pulls the correct pre-calculated matrix.
Which is brilliant.
The metric they achieved is almost difficult to comprehend, a 10 billion-fold speedup in tsunami forecasting. They're generating precise wave results in under 0.2 seconds.
Pre-computing those massive wave matrices on GPUs isn't just a computational flex. When you are dealing with a tsunami, you aren't just calculating data, you are buying time.
Right, real lives are at stake.
Exactly. AI is no longer just generating text. Brute force GPU parallelism is literally solving planetary defense in real time.
It is incredible.
Yeah.
But this brings us to a massive point of friction. If researchers are bending math to create infinite memory, autonomous steering, and real-time planetary physics, the developers out there trying to build consumer applications with these tools are suddenly hitting a brick wall.
Yeah, the pipes just aren't big enough to handle it.
Between April 19th and April 25th, that friction became painfully visible. On the global NVIDIA developer forums, we saw what amounted to a platform meltdown.
Oh, it was a mess.
The headline across the community was Agentic AI Rate Limit Surge. Developers flooded the boards demanding that NVIDIA increase the base API rate limits for NIMDO, which is NVIDIA's inference microservice.
Right.
The base limit was 40 requests per minute, and developers were desperately begging for an increase to 200 requests per minute.
Which makes perfect sense when you consider the shift we talked about at the beginning.
Yeah.
If a human is typing prompts into a chatbot, 40 requests a minute is plenty. You physically cannot type that fast.
Imagine you're trying to manage a team of 50 hyperactive digital interns, but your software only lets you talk to one every few seconds.
Exactly. If you build a multi-agent swarm, say, one agent reads a massive document, passes it to 5 researcher agents, who then pass their findings to 3 writer agents, they are all pulling the API simultaneously.
And hitting that wall immediately triggers a 429 too many requests error.
Yep. And at the same time, developers were facing SMS verification blocks on the build.nvidia.com platform, particularly those using international numbers with a +86 country code.
So developers were just getting blocked at every turn.
Yeah. But this friction isn't just a technical glitch. It acts as a massive macroeconomic indicator. It proves the baseline metric of AI utility has permanently shifted from human speed single prompts to machine speed parallel processing.
The industry has officially moved to parallel swarms.
Exactly.
And to handle that kind of parallel swarm demand, you need models that are incredibly efficient. Which brings us to the software updates we saw for the new hardware. On April 24th, via the NVIDIA technical blog, we saw a headline announcing Day Zero Blackwell support for DeepSeek V4.
This is a big deal.
NVIDIA confirmed full Day Zero support for both DeepSeek V4 Pro, which is a massive 1.6 trillion parameter model, and V4 Flash, a 284 billion parameter model.
Delivering 150 plus tokens per second per user for those models on GB200 NVL72 systems is a staggering technical achievement. And that day zero distinction is a critical competitive moat for NVIDIA.
Because if the hardware can't run the newest, most advanced open-weight models flawlessly on the exact day they launch, it's essentially just an expensive space heater, right?
Precisely. Sustaining inference dominance for a frontier 1 million context model on launch day proves that NVIDIA's software stack is just as robust, if not more so, than its silicon.
But wait, if developers are suddenly bombarding APIs to run massive swarms of trillion parameter agents, the physical data centers hosting them must be melting down. How does the hardware layer adapt to this sudden exponential spike in parallel demand?
Well, it requires an entirely new architecture. At the Google Cloud Next event in the US on April 22nd, we saw a joint announcement.
The Vera Rubin announcement.
Right. The headline was Vera Rubin A5X bare metal instances. Google Cloud announced these new instances are powered by NVIDIA Vera Rubin NVL72 rack scale systems, and they are supporting multi-site clusters of up to 960,000 Rubin GPUs.
Hold on, let's pause for a second. 960,000 GPUs. Here's where it gets really interesting. For those of us not actively racking servers in a data center, what does bare metal actually mean for those AI agents?
So in traditional cloud computing, there is usually a virtualization layer. It's software that divides a physical server into multiple virtual machines. It adds flexibility, but also adds computational overhead.
So it slows things down.
Yeah. Right. Bare metal means stripping away that virtualization layer completely. The developer gets direct, unshared access to the raw physical hardware, which is absolutely necessary when you are trying to squeeze every ounce of performance out of a multi-agent swarm.
And the performance claims they are making with this raw access are fascinating. They claim this architecture delivers up to 10x lower inference cost per token and 10x higher token throughput per megawatt compared to the prior generation. I want to focus on that phrase, throughput per megawatt.
It is arguably the single most important metric in the tech sector today.
Why is that?
Because we have essentially reached the limits of the traditional power grid. You cannot simply build larger data centers indefinitely because the raw electricity just does not exist to power them.
Oh, wow.
So if your power budget is capped, the only way to scale your AI operations is to get more intelligence out of the exact same amount of electricity. Increasing token throughput per megawatt by 10x alters the fundamental unit economics of running an AI factory.
That makes total sense. If the global economy is going to require this much physical infrastructure and electricity, where are we actually building these systems?
That is the big question right now.
And that brings us to a historic manufacturing update. On April 20th, tracked by global outlets like AFP and News of Bahrain, the headline was Historic U.S. AI Supercomputer Chip Manufacturing. CEO Jensen Huang announced that NVIDIA will manufacture its most advanced AI supercomputer chips entirely within the U.S.
Yeah, the projections are massive. They are aiming for up to $500 billion in U.S.-made AI infrastructure by the end of the decade, in partnership with companies like TSMC and Foxconn.
Moving semiconductor packaging to Arizona and Texas is a historic shift.
It really is. Bringing advanced AI chip packaging onshore represents a radical shift in global supply chains. It strengthens resilience against global disruptions and aligns directly with broader geopolitical tech strategies. When compute becomes a primary utility driving the economy, controlling the physical manufacturing of that utility becomes a core element of national security.
But controlling where the physical chips are made is only one part of the equation, right? Controlling where they are allowed to go is entirely different.
Definitely.
On April 22nd, a Reuters report highlighted the H200 AI chip export status to China. Now, we are simply looking at the objective facts of this trade dynamic to understand the flow of compute here. During a congressional hearing, U.S. Commerce Secretary Howard Lutnick testified about the current status of these shipments.
Right, and the facts on the ground are that the U.S. granted conditional approval back in January for NVIDIA to sell the advanced H200 AI chips to China.
Okay.
However, Secretary Lutnick's testimony revealed that NVIDIA has not yet sold any of those chips in that market.
And why is that?
The reason stated was that the Chinese central government has not allowed local buyers to purchase them.
It just illustrates a deeply complex geopolitical landscape. It shows that even after domestic export regulations are cleared and conditions are met, foreign government policies can effectively block market access to advanced accelerators.
It really shows that international chip policy is as impactful as the hardware itself. Securing the geographical borders of hardware is step one, but step two is securing the software borders.
What do you mean by that?
Well, if enterprises are going to deploy these autonomous swarms, especially given current geopolitical tensions, how do they ensure the agents don't hallucinate, leak data, or execute a catastrophic action?
Right, that is the exact problem addressed on April 20th. A global NVIDIA blog post ran the headline, Autonomous AI at Scale with NVIDIA OpenShell. NVIDIA announced an expanded strategic collaboration with Adobe and WPP.
WPP being one of the largest advertising agencies in the world.
Exactly. They are integrating agentic AI using NVIDIA OpenShell, which is a new policy-based, containerized, secure runtime for AI agents. And interestingly, at the exact same time, NVIDIA deprecated its open source safety for agentic AI repository.
Moving away from fragmented open source safety patches into a standardized, enforceable runtime environment is a massive enterprise signal. OpenShell solves the enterprise tension between generation speed and brand safety.
How does it actually do that?
It ensures that any autonomous agent is strictly governed, fully auditable, and confined by runtime protections.
It's like putting heavy-duty bumper bowling rails on a super intelligent digital intern. But in this case, it's not just a suggestion for the AI. It's a hard physical software limit built into the lane itself.
That's a great way to put it. A major agency like WPP absolutely requires this before letting an AI touch a global brand campaign. They cannot afford to have an agent accidentally launch a controversial ad because it got confused. The guardrails have to be unbreakable.
And once you put those secure bumper rails in place, enterprises are finally comfortable letting these agents run wild in the real world.
Exactly. And the most compelling case study we saw this week came from inside NVIDIA's own walls.
Yes, I love this detail. On April 23rd, the NVIDIA blog published GPT-5.5 Codex on GB200 NVL72. NVIDIA disclosed that OpenAI's Codex, powered by the new GPT-5.5 model, is running internally on their own GB200 systems.
It's incredible.
It is currently being utilized by over 10,000 NVIDIA employees across all corporate functions, from engineering to HR and legal. NVIDIA is using its own hardware to run an OpenAI agent to help its employees build better hardware.
It is the ultimate proof of concept, and the internal metrics validate the architectural shifts we discussed earlier. This internal deployment yielded a 35x lower cost per million tokens.
And crucially, it resulted in a 50x increase in token output per megawatt.
Yeah, that 50x metric is the definitive proof that token economics finally make large-scale agentic swarms profitable. You simply could not deploy an agentic workflow to 10,000 employees if it bankrupted your corporate power budget.
And this transition isn't just happening on corporate screens, it is actively moving into the physical world. On April 20th, opening the Hannover Messe trade fair in Germany, NVIDIA showcased physical AI moving from pilot programs to actual production.
The industrial AI shift.
Right. The headline focused on the industrial AI cloud. Deutsche Telekom showcased a 10,000 GPU industrial AI cloud. But the centerpiece was the humanoid HMND-01 robot running on the Jetson Thor platform.
This is where all the math, the models, and the infrastructure converge. If we connect this to the bigger picture, we aren't just talking about chatbots anymore. We are talking about 60 physical boxes moved per hour by a robot with an AI brain.
The humanoid achieved a measurable 60 tote moves per hour on a real Siemens factory floor.
It proves the viability of NVIDIA's full physical AI stack in heavy industry. The robot perceives its environment, it reasons about its goals using the test time alignment frameworks we explored earlier, and it physically manipulates objects.
It really brings the entire week into focus. Let's trace the path we've been on in this deep dive. We started with researchers completely rewiring LLM memory so an AI can read and learn without slowing down.
Right.
We saw the math behind giving those models a steering wheel to correct their own reasoning. We watched developers beg for higher API limits because they are unleashing swarms of these digital workers. We looked at almost 1 million GPUs being deployed to support those swarms, optimizing every single megawatt of power.
Yeah, the scale is just unprecedented.
We navigated the geopolitics of U.S. manufacturing and global export blocks. We saw unbreakable software guardrails put in place for massive ad agencies. And finally, we saw humanoids working in German factories.
It is a remarkable convergence. It proves the shift from transactional chatbots to autonomous infrastructure is complete. And it brings up a vital question for anyone trying to navigate this new landscape. If the AI industry has officially shifted from prompt engineering to simply defining high-level goals for swarms of autonomous agents, what happens to human workflows when the AI starts setting its own sub-goals to achieve your requests?
Wow, that is a thought that is going to keep me up at night.
Yeah.
The vending machine is officially closed. The autonomous factory is open for business. Thank you so much for joining us on this deep dive. Think about how you are going to utilize your own agentic swarm in the near future, because the tools are finally here. We will see you next time.